Hello, everyone. So here I'm going to be talking about process injection shellcode using system calls. So here I have a list of all the APIs I'm going to use here in this shellcode. And we're going to start with the first one, which is NT query system information. So the purpose of this API is to give all the necessary information about the running processes in the background. So the reason we do this is we need to get the process ID or the process number of the targeted process that we are using to inject our shellcode into. So this API has a system information class and it has many other classes, but the system information class is telling the API what kind of information you need from the operating system. So here I'm using system process information, which is equivalent to 5, the value in hex. So this is telling the operating system we're only interested in information about running processes. Once we get that, so we can parse through each process and we can get the process name and the process ID. So this is what the system process information structure looks like. The first element is called next entry offset, which is pointing to the next process. And the other one is called image name, which is the process name. And that's the one that we are interested in because we know the process ID is changing, but the process name, it doesn't change. So we need to look for the process by looking up its name. And the last one at the bottom, it's called unique process ID or the process ID. And this is the one that we're doing all of that to get. Here we have the system information, system process information. This is just an example. A process called system. It's a Unicode process name. So you make sure when you're doing this, a Unicode string has null bytes between each character. At the top, the next process is at offset 0. This is what we use to go through each process in the data that we get. Offset 3C has the process name and offset 4E4 has the process ID. So the way this works is we don't know how much data all the processes running in the background would be. So we can allocate arbitrary value using something like NT allocate virtual memory. And we call the NT query system information, and that might not give us a success value as a return. So what we do here is we allocate more memory, which is like, let's say 2000 in hex or something. And then we call the same API again. Once we get a successful value back, that means we have all the data that we want, and we can parse through each process using the same thing that I just discussed here, the process ID and the name and all of that. Once we have the process ID, we can move forward with the NT open process. Very straightforward. It takes 4 arguments. One of them is called object attributes. The object attributes here is another structure that we're not we're not using most of it. We just need the length. Everything else should be zeros, like the root directory, object name, all of that could be used for other stuff, but not for this case. And we also have the client ID or PC client ID here. This is the process ID we just obtained. So we will use that. We also have the desired access, which is all access, 1 on 5Fs in hex. And the variable at the top, the process handle, this is to receive the handle for the process. Once we are done and we opened the process, we have a handle, we can keep going with the NT allocate virtual memory. This API is like the godfather of the virtual alloc and all its variants. It's very similar to virtual alloc. The only difference here is the base address, like the second argument, it's in and out. Like this variable will be used to get back the allocated address in memory, and we will use that later to write our shellcode. The process handle, the one that we just got before, and the 0 bits is just zeros. It's kind of optional here. So we have the region size, which is the size of the shellcode. We have the allocation type and the protect, very similar to virtual alloc. This is just an example of what it looks like. The first one is the protect, like the page, execute, read and raw, what kind of permissions you need to get, and the type, the reserve or commit or both. And the rest of the things here, like the size of the shellcode and what I just discussed. And finally, we invoke the system call to make it happen. Next, we allocated some memory in the remote process. Now we need to write our data there. We need to write the shellcode, which is I'm using interpreter shellcode here in this case. So here, very straightforward, same thing. We have the process handle, we have the base address, which is the pointer of the allocated space in the remote process. We have the buffer, which is a pointer to the shellcode that we have in our C program, like the interpreter shellcode. And the size of the shellcode, it's a number of bytes to write. And the last one is optional. This is the number of bytes you get back, like how many writes you were able to successfully write to the remote process. Once we're done, this is like the shellcode, same thing. We invoke the system call to make it happen and write the interpreter shellcode to the remote process. And here, once we have the shellcode written to the remote process, we spawn a thread from the process using int create thread, the extended version of it. In this API, it takes 11 arguments, but actually the last 6 arguments are zeros. They're optional, and we don't need them in this case. We're only interested in the first 5, the p handle of the thread. This is like a handle, like a variable to receive a handle for a thread, which is not really going to be used. The second one is the desired access. Same thing, we're using all access, which is 1 and 5fs in hex. And we have the object attributes, same thing as the int-open process. We're only using the length, and we're not using anything else in this structure. And then we have the process handle that we keep using all the time. And then we have the LP start address, which is an interpreter shellcode address that we were able to write to the remote process. This is what it looks like in shellcoding. This is an example. So the shellcode pointer to the, I'm using a tool called crypttool.exe. You can use anything else you want. Just make sure when you're doing this, if you compiled your file using 32-bit and you want to inject something into another process, make sure the process has 32-bit architecture. Otherwise, you will get access violation. So now we have 2 separate shellcodes. One is for system call shellcode, and the other one is the interpreter shellcode that is hiding in your C program. But now, we need to combine those shellcodes together so we can use them, if you're leveraging a vulnerability or something, and if you want to execute them at once. So here at the top, I have the green part at the top. This is just used to get the beginning of the interpreter shellcode. I'm using the call pop technique here just to get the address of the interpreter shellcode, and then I jump down all the way down to the green part at the bottom, which is the start of the system call shellcode. So now once you have this large shellcode, a combination between system call shellcode and interpreter is sandwiched between them, we need to execute it somehow. So you can execute this in memory if you have a vulnerability, or you can just have a C program if you're running a malware. And you can use a shellcode tester if you want, but if you do that, you'll still use some kernel 32 APIs. So I wrote this execution skeleton to do that, so you can avoid kernel 32 APIs. It's equivalent to the one that you can use virtual alloc and then memcopy. This one is still using the same system calls. You're still using int allocate and int write to write the shellcode to memory. And then the last line at the bottom is jump to this place and start executing. So it's demo time. So this is the tool I just started, and then now I'm going to start a debugger just to show you the stuff, how it works in the debugger. Oh. Yeah. Why it doesn't?
Like 1 minute. How would this run?
Okay, it's ready.
So here I'm using the cryptool.exe, the one that I just mentioned. And this is a debugger, X32 debug. So the first breakpoint is where we get the actual cryptool.exe. Like we found the process here at the right side. And then now we can parse through the process and we get the process ID. This is just to verify the process ID that I got is the same using task list. Convert the hex to a decimal so we can get, just to verify it's the same process. The second breakpoint will be when we allocate the memory into the remote process. Here we have the allocated space at 18E4 zeros. We open process hacker to make sure it's the same. It's there. We have the read, write, execute permissions. I'm sorry. And the last part here just showing the Windows Defender is up and running, and we run it and we get Metropoder shell back. And as you can see here, Windows Defender was just taking a nap. It's not doing anything.